right, we are now recording, and for those people offline, I just gave a quiz just to think about a point, and that is, here we go. Write a function to take an inputted character, examine it, and if it is lowercase letter, make it a capital letter. Now, actually, I put a specification in there. You have to examine it, all right? Which means that you don't just assume that the input character is going to be a lowercase letter, because it may be a space. It may be a capital letter already. Or it may be some other funky character, exclamation point, whatever. Or it may not even be printable. And so, following the spec, you have to examine it, make it a capital letter. Notice I didn't tell you how you could do it, right? And so, the result was this code down here. And actually, if I did this, I didn't even need the pound defines in there. And as we discussed in class, since I didn't specify how you converted it from a lowercase to an uppercase, you could also put in here that letter minus 32 or letter minus hex 20 would do the same thing, and that's acceptable as well. But that leads us to, and then people were talking about, oh yeah, I forgot to put in the return. Return would be helpful because you're trying to return a function, right? Or I forgot to do this or that or the other thing. And that's really important, and a lot of that stuff can be caught in the process of going through a disciplined software development environment. And so, with that in mind, we're going to address that with our next section. Software engineering for embedded systems. So, the objective, and this is chapter 5 in our book, is to examine how you should develop software for embedded systems. In particular, structured development process. We're going to look at the overview, stages lifecycle model that they have been using for many years, and in fact, it's pretty prevalent in some Department of Defense documentation that I've seen. Why do you need to do it? Well, consider this. Software, all software will have bugs in it. I don't know why, but that's just the set of nature. A good example, our university has now moved everything off to Gmail, right? And all their wonderful tools like Google Calendar and Contacts, etc. I don't know what it is, but Google Contacts just does not work for me. I can't get it to refresh, for example, if I add somebody's name to a distribution list. That sounds like a bug. Now, in embedded systems, there are situations where something might need to be rebooted. In one of the articles that I've had the class read in the past, there was a fan that was above a stove that had two simple switches. One was for the light, one was for the fan. And somehow, that entire hood got into some mode where the switches just would not work. And it's a simple fan. It has a light. It has a fan. It sits above a cooking stove and carries out the fumes from your the different things that you cook that you might burn. So the only way that this gentleman could fix it was to walk out in his garage to his breaker box and turn off the power to the stove hood that ran the fan, turn it back on. Basically, he did a power on reset, and it worked. So even in simple things, you might get a mode where there's a bug in there. And so when you have this unexpected behavior per peripherals and budget constraints, you're going to really appreciate the need for a structured development process, because also if you develop good code, It will be easy to maintain in the future should you have some sort of problem, or should you need to also update it for additional features. And so we're going to talk about the structured process to reduce risks in our software development. So if you think about the stages of embedded systems lifecycle, some salespeople, might be engineers, will identify that there's a need to do something. Oh yeah, I could see we need to do that right there. And so they'll develop the concept, they'll design the project. At the same time, the manufacturers are designing how it will be built. You'll produce it, you'll deploy it, and this actually is a surprisingly common thing that you'll have to do, is support this product for sometimes a very long time, maybe make some upgrades, and then eventually retire or dispose it. A good example, I have some pretty old, what is it, the Apple device that plays iPod. The iPod, right? I got the iPod. In fact, I got one that has a hard drive in it. They used to do that before they were able to put a lot of the songs on solid state memory. And I don't think they make an iPod that has a hard drive on it anymore, do they? No, too expensive, breaks too much because it's a moving part. And so eventually you're going to have to retire it or dispose it. But one thing they have done is they've taken iPhones and they have upgraded it or identified how you can change it to allow it to run a little bit longer. And sometimes that happens. See that up there? That projector will probably be up there for about 15 years. And eventually it will have to be replaced because it will have just burned out or something else like that. The expectation is, though, that that thing may never get new code, but it may get new code. I bet you it has a USB port on it that allows you to upgrade the code if it really needs it. So if we look at a model for developing, this V is very, very, very common in all fields of engineering and development. You start with requirements, developing requirements, identifying what is your best requirement. We're going to do some of that here in a few minutes. Then you identify the specifications. In other words, you're going to specify how your product will work. Then you will identify the general architectural design of your software. You'll design it in more detail with algorithms, flowcharts, etc. You will code it, and then you will test small pieces of code alone. Then you'll put several pieces of code together and test that, and then maybe you'll integrate the code with the hardware and test that, and then finally you will functionally test your eventual device. Each one of these stages over on this side is the validation to, did I write my requirements and specifications correctly? Did I design the architecture correctly? Did I code directly? Now notice that at each one there's a step called review, and based on input for the review, you should modify it. So I'll give you a good example of something that I did when I was at IBM and I worked on the space shuttle program. I actually wrote some software that flew in the space shuttle. The space shuttle actually had 3 total different loads of code. One for launch, one for orbit, and one for descent and landing. And so mine was for orbit, so I'm not responsible for any crashes. The code was for communicating between the space shuttle and a payload. The payload was called Space Lab. Darned, I had to go through every single one of these steps, and along the way we had a review all the way, and in the end I thought it would be a lot of code, but through the reviews, it turned out to be only 6 lines of code that I had to add. All right. Apparently, they had a lot of functions that were available for doing a lot of the work that I expected. And that's why we had reviews, is because I had somebody who was more experienced able to say, you need to look at that over there. And based on that, I was able to avoid taking up, maybe 2 or 3 kilobytes of code, and instead it only took about 15 bytes of code because I didn't rewrite a couple of functions. And that's why we have a process that includes a lot of review or peer review. So if we look at the stages, the requirements, design before coding, peer review, system architecture and design, detailed design, implementation, software testing. So requirements. This is very important with respect to any project that you work on. Clearly written so that every team member has an idea of what's expected. In other words, what you are identifying is the functionality of your device. You're also identifying the expected performance, or maybe even constraining the system to use certain technologies. That may be a requirement of your customer. So functional will be the expected functionality, behavior, response time, and energy efficiency, and then, as I said, constraints, limits like cost or particular technologies. So what I would like to do is I would like you to think about the following type of application. And no better time to have you do some hands-on work. So let's do it. I'm going to have this device for my bicycle. So bicycle performance monitor. This bicycle performance monitor will be expected to record the speed that I'm riding and the distance. Now you'll need different inputs and outputs. You'll need to store different things. Some inherently obvious things that you have to worry about is you're probably going to have a time of day clock, right? Some way to measure distance. So what I want you to do is to get in groups of 4. So groups of 4. And should I make this a quiz? What do you mean no? Don't forget, the more quizzes you have, the better you do. You could drop some later, right? All right.
You won't have more than 20 quizzes, I guess. It's going to be very difficult to make more than 20 quizzes.
Oh, it's going to be really difficult to have more than 20 quizzes?
Yeah, 20, yeah.
Ah, so this is quiz number 8. And we just had 7 a few minutes ago, right? Are you sure?
Yeah.
Oh, okay. Well, I'll have to check on that. All right, then we'll have another one. Great. This will be a quiz. So I want you to spend a little bit of time to write down some requirements for this bicycle performance. All right, welcome back. Our exercise was just to write down the requirements for an application, and so I got lots of. Just to recap, I should say, we talked about requirements, architectural design, detailed design, coding. Notice that requirements are done all the way at the beginning because you don't know what you're going to do before you start doing it. So you have to actually write down on paper your intention. How are you going to have this system operate? Because you can't design if you don't have that. Going through detailed design, coding, and then all the way back up the board. Now, this shows just software, but very often at the same exact time, you're developing the hardware. And sometimes you have, like the Renaissance board is an evaluation board that allows you to write some software and kind of pretend that you have a hardware system. And sometimes that's all you have because somebody is developing the actual hardware product, and they're going to be done at about the same time that the code is ready. And so you have the evaluation board that you can use to write the code and the applications. And then when you get down here, then you start introducing the code to the actual board, and you're kind of debugging the board and the software at the same time. That is called, when you develop both hardware and software at the same time, co-design. Co-design. That sounds like a great quiz question. So, when you start having unit testing, you'll actually use the firmware that you develop to exercise bits of the hardware. But you don't have a lot of complexity with the software. And as you integrate more and more and more, like the full software package with hardware that's been actually verified, then you'll be able to identify that, yeah, we have made a correction to the hardware or a correction to the software to allow both to work together. Eventually, you're going to validate the original requirements of your entire system to make sure it does what it's supposed to do. So like that little bicycle unit that you did requirements for. Did you say something along the lines of using buttons input the time of day? Did anybody think about you've got to have a clock? Maybe it'd be nice to have the time of day that you have to enter in?
A timer, not necessarily.
So some of you designed it as a timer. Interesting. And how would you start the timer?
It was a button.
All right, so you included when a button is pressed, start your bike ride, right? Okay, there you go. So concepts like that. By the way, the cheapest, well, here's a question. How inexpensive is it, the difference between a time of day application and just a regular old timer? Do you think it'd be more hardware, more cost? All right, so is that more cost? What do you think? Well, it depends on your chip. Some chips have it already built in. And you're going to have the same concept where you'll have to keep track of time. And so the time of day clock will do that for you automatically. It'll update every second, actually probably every millisecond. Otherwise, you'll have to write software for that. So sometimes knowing that up front, like are you going to have a timer or you're going to have a time of day clock, is important because then you'll have, that'll determine how your design is done later, right? So we started out with, as we said, requirements. Then we're going to go to the design before coding. And you have to understand all the parts of the system to know how complex it's going to be. So you could use graphical representations, or you can use concept like pseudocode, right? To be able to do that. But remember, it's too early yet to code. So that's the problem that a lot of you have, or I should say a lot of original or beginner designers have, is that they want to start getting their hands dirty in the code way too early before they actually identify what's going to go on. In the process, or in the along the way of developing a product, you often have what's called peer review. And we saw a picture of this in the graph. Notice that there's a review at just about every step. And the reason for that is that a peer review will allow other eyes to take a look at the code associated with whatever your application is, or the design of whatever your application is, or the requirements of whatever your application is. So let's take a good example. I am going to develop a system, and it's going to be very similar to what we had the assignment. So one of my requirements is the unit shall display information to the bicycle user. I don't include anything, any detail, right? The display shall show time of day. The display shall show mileage ridden. The display shall show miles per hour. We're in the US, so we don't really believe in metric. All right. Nobody snickered. Oh my gosh. The user can switch the display between the three modes by pressing a button. Let's say that those are my requirements. So we now open up a code review. I am the reviewer. I'm sorry, I am the author of this. You're a strong personality. Come on up. Have a seat. And do I have another volunteer for a trip to the prize closet? You're going to be the recorder. Who wants to do that? Come on, somebody. All right, you're up. So I'm going to actually switch roles. And let's pretend you wrote that. Is that okay?
Nicer handwriting than mine.
Okay, we'll just do that. All right, so I'm going to be you're the author, you're the recorder, I am the review leader, and all of you are the reviewers. All right, and so one thing I should have asked: how's your handwriting?
Pretty good.
Pretty good. Good. You're the recorder, and you will record all suggestions from the people. I'll give you a nice, since it's a problem, we'll give her red. No Snickers either. Come on, people. I should say, Pranay, can you see everybody, or do I need to? Okay. Can you see them instead of heads? Okay. So today we're going to review the requirements for the bicycle speed and distance reporting device. And so we have our recorder and we have our author. Do we have any comments about requirement 1?
I have one that matters.
Go ahead.
It kind of ties in with 2. It could be separated out a different way, I think.
Okay. So he's thinking about a separate way. Does anybody have any observations or suggestions then?
I guess information is pretty ambiguous.
So requirement 1 is ambiguous. Yes. Are you thinking what is the ambiguous aspect of it?
like information, which is given like in R2, R3, R4.
Okay.
And there it's just information. It doesn't really.
It doesn't say what information.
Yeah.
All right, so it's a bit ambiguous, but requirements 2, 3, and 4 do kind of have some information. So perhaps the unit shall have a 8-character display, which will show different types of information to the bicycle user. All right, so perhaps we can add that in. Now, typically, I'm going to step back from the leadership role. You don't want to get too detailed about the display. But sometimes you do. For example, if one of the aspects of this is cost, or the previous product had an 8-character display that only displayed, it only had a timer, so it only had speed and miles ridden. So maybe you want to ensure that you have more information or more characters to allow it to be displayed. All right? Any other comments on requirement 1? Any comments on requirement 2? Yes, sir.
Detail about time should be provided, that it's AM or PM or 24 hours.
Okay, so again, sometimes it's going to be an implementation detail, but I think at this point we could say that the display shall show the time of the day and then add to that in the format of HH, MM, SS, and in parenthesis we'll say 24-hour clock. Does that seem acceptable? Is that something you could do? You're playing the role very good, thank you. And do we have any comments on requirement 3?
Overall mileage or just
Per day or overall, or starts from
total
when?
mileage or
Oh, so we're not being very specific about what we're saying. So, and in fact, so if we were to add, since distance was reset, would that be acceptable? Now I'm going to add another change or another suggestion for the requirements. Our product we want to sell in the US, Canada, and other places too. And since US is the only place that has mileage, perhaps we should change this to distance, all right? So, and then that means later on we might have to add a requirement to switch between the mode of miles or kilometers, all right? All right, so y'all got a pretty good flavor of what this was, and are you done? Good enough. Thank you very much. You have a trip to the prize closet. Have you been to the prize closet before? You know what? You can go again, just for grins. All right, let's give a round of applause for our volunteers. The box is over there in the corner. You could go grab it. And I don't know, I might not have replenished it, so the prizes might kind of suck. All right, so our recorder. Oh, she got something anyhow. All right, you chose nothing.
I'll take a look at it in a minute.
Yeah, all right, in a minute. So our recorder, of course, would put this in computer format, and he or she will make comments with respect to what was discussed at the review meeting, all right? And this was just a little example. By the way, at a review meeting, really you want no more than 4 people. And it could be that the recorder and the team lead also are reviewers of the design, requirements, code, whatever. So this is an example. By the way, I had a manager who once said that nobody wants to be told that their child is ugly. And, you know, even though you didn't really design it, you know, you have to be, this is the best way to put it, respectful of the designer whose material you are reviewing. Hence, you don't want to create an adversarial environment in your review. Actually, I sat in a code review where a guy I shared an office with was very adversarial, and it was not pretty, and they actually kind of argued a bit, and I sat back and observed it all and said, I'll never do that. Good example, good example. Let's continue on. So once you have the general requirements, then you do what I call system architecture and design. So the system architecture is going to identify, the processor and peripherals. So I should say hardware system. But there's also a software system architecture. So the software system architecture is going to split up the code in different pieces. So a good example of this is, let's do the system hardware architecture out loud, all right? We should have what type of a processor? 16-bit processor. I'm not even, we're at the system architecture, so I could actually define which one. And based on our tools, it will be the MSP 430 because we have the existing tools and expertise. And peripherals. So what kind of peripheral do we definitely need? An LCD, correct? How many characters wide? 8. We already said that in the requirements. And then we had buttons. Anything else? RTC. But the processor may have that already, right? So we have to ensure that when we specify the processor, that we say choose an MSP that has a real-time clock on it, and they exist. All right. What else do we need?
We need a sensor to measure times.
The sensor. All right. Which what did we determine we might have to have?
Mileage. Distance.
A what?
Revolutions for.
Yeah, so we have to find some way to detect what those revolutions are per second, right?
For the distance, right?
For the distance. Or you have to weigh, actually there's 2 aspects of this, right?
Speed.
You have to have a sensor that attaches to the wheel to know exactly how many times you revolve. Do you think an accelerometer will do that?
Rotary encoder.
Accelerometer may not do that, right? But, GPS will tell you though, won't it?
Yeah.
Oh, but you just increase the cost dramatically for your device. So we need some sort of encoder, but there's another device that's really easy, which would be a Hall effect sensor. Just basically when a magnet passes a sensor, there it goes like that, all right? But that means that you need to wire something. Is that okay? Do you think you could wire something? Yeah, it's probably not a big problem. Attach something to one of the spokes and mount it somewhere down and run the wire up to the handlebars. All right, so that's how you identify you're going to do it.
How about infrared, photodiode and infrared or something like that?
Oh, you could do a photodiode counting the spokes.
No, it will be one on the side of the wheel and one on the other part. So it will, whenever it passes, it will.
Okay, so you're going to have to find a way to occlude that, like with like a piece of paper or a piece of plastic or something. Okay, that's another idea. All right, but actually, this is the step where you determine what that is. There's one other big thing you're missing.
What about gears?
What about what?
Gears, like gear cycles. Give one first gear, second gear.
No, okay. Do you think that makes a difference? Does that affect how many times the wheel rotates? Well, your gears affect it, but you're really measuring distance, which is the wheel, how many times it goes around, right? So the gears really don't make that much of a difference. What else? You've got to speak louder.
You need to multiply with the circumference of the wheel to get the distance rather.
Oh yeah, well that's processor, it does inside, right? So that's going to be code, we'll do that later. How about a battery? You want a battery? Okay, so I think a battery would be pretty good. And then you also have to determine, is this going to be a rechargeable battery? So how do I recharge it? Say that again?
Dynamo.
Ooh, yeah, but that just now adds a lot of cost, right?
Better to use a pencil cell and then use a booster to power the devices. So
Okay.
use replaceable.
By the way, anybody familiar with this? Right? Yeah, I know I've talked about it and I bragged, all right? By the way, should I bring this with me to India or should I leave it at home?
Might get stolen.
Yeah, might get stolen, okay. This charges by sitting on a capacitively charged puck. So there's no plug in this to charge it. Or maybe you do it with USB. That you cover kind of like with your phone. All right, so now let's look at the software architecture. And I think we've already identified that. In fact, this would be a good time to figure out what is the functionality of the main functions you might want to run with your application. So turn to your neighbor. Maybe there were 3 or 4 of you who did the requirements. Identify what major functions, C functions, all right? You're not writing the functions. You're just saying, all right, we need the function that does this, the function that does this, the function that does this. Major things, all right? Between you and your 2 or 3 other people, determine what that is, and I'll show them up front. All right, so here we go. Here's one group's, look at this. Function to calculate speed in miles per hour. Actually, it would be speed in whatever you have decided it's going to be. Function to send data to display. Time of day, charge status of the battery. So I would be a little bit go further. I would say calc speed, calculate speed of bike in appropriate units. And let's see, display, display characters, on LCD, and TOD, get correct time of day, and 4, charge status, get the percentage of battery capacity and charging status. 5, and on and on and on and on. You're going to have a lot more of this, right? Then, of course, you're going to have one of the other ones is going to be main function of device. But the expectation is that all the functionality of your bicycle timer, in this case, is going to be represented by one of these functions, one of these, the concepts associated with, let me see if this, that looks like it focused better. One of these functions, and as I said, not everything that you want this bicycle timer to do is actually represented up there. You're going to have to include a lot more than this, but that's a good start. You never know when you'll have to answer a question like that on the midterm exam. Hint, hint. All right, so I get to roam around and hand this back, but you can still hear my voice as the screen is up there. Just keep it over there. Is detailed design. So now that you know what your function is, you can actually write the detailed design. And the detailed design would be the subsystems of the architecture. So you could divide it into functions and ISRs and actually identify with algorithm what it's going to do. So the time of day one or the charging one, you would actually say, read this, read this, read this, do this, return this. But it wouldn't be code. Remember, it's an algorithm. So you have to take that in and write the flow charts or algorithm with respect to the designs and constraints that you said earlier. And I'm not going to go into that in great detail right now. Implementation is called coding. Now, hopefully, you have learned in the process that when you write code, first of all, you should be doing all of those steps first before you ever write code. And then when you write code, you do it slowly. So remember that V all the way at the beginning. Remember that software unit testing. Unit testing means you're testing what? What kind of code? Like an individual function, a little piece. And in fact, in some cases, it may only be part of a function. But the important thing to note is that you should test each one of these functions separately. And in fact, in many cases, you can write the code for the function and then test the code for the function and then set it aside or actually use it for the next function, because very often several of these functions depend on each other. And the best thing to do is to debug an individual function and verify that it works completely correct before you join it to another function. Because the problem that students often have is what they call code and pray, all right? You throw it all in one file, and then you hit the compile, and then you never know if it actually compiles or if it's running correctly. So, and when it doesn't run correctly, you don't know where to start looking for the problem, right? However, if you do one function at a time, you're kind of limited within a few lines of code what actually needs to be looked at. So it is much, 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 much better for you to go ahead and do one function at a time, write it, and then debug it. Oh, it's here in the implementation. And then testing. Well, it's impossible to create error-free code unless you have like one line. And even in one line, you might have an error, right? So the verification will allow you to test all of the functionalities. And again, when you start combining these functions together, you might get different characteristics of functionality than what you had anticipated. And so there are two basic ways of doing the functional testing or the integration testing towards the end. One is called black box. Well, actually, you could do this at a lower level too with individual units. Black box means that you have no idea how something runs inside, and you just give it input, stimuli, and then you expect a certain output. White box testing relies on the knowledge of how the software flows inside, and the tester will actually make sure that they go through all the lines of code with all the possible ranges of values that that code could have. And then there is another type of testing which is called regression testing. And that's when, if I observed a bug in one piece of code and somebody fixed it, or I fixed it, I want to go back and test that again just to make sure that I didn't break it later on. So I'll continue to test that situation later on. We talked about software development lifecycle models. By the way, there is a complete software testing set of slides that I go through, and I'll do that later. There are all sorts of different development cycles to use, everything from iterative to spiral to agile. And for example, I used something called Waterfall. And Waterfall means that you finish one thing completely, like requirements, and then you finish the next one, kind of falls into the next, which would be the specification. Then you would finish that completely for your entire product or project, and then you would get to the next step, which would be detailed design, and then you would go to the next step, which is the coding. And one just falls into each other. So the waterfall needs, requirements, design, build, test, user, product. One falls into the other. Now, typically when you're inside that, you do have reviewing, but there's really no feedback up the line. Contrast that with something that is more iterative, and that is, I need to fix this slide. It needs to be more of a sawtooth. So in other words, you go through remember that V? You go through the V, and then you go through another V, and then you go through another V. And each one of those V's is additional functionality of the project. So let me give an example of a mobile phone. Let's say I'm developing a new mobile phone. And I'm going to develop an extremely inexpensive phone. No smart capabilities whatsoever, right? So it's going to have only a few functionalities. So probably the first thing I would want to test is if I can actually use the screen to enter in a number. And I would do that. And that would be the first thing I would build and come back. There it works. Then the next iteration is, does that entered number, first of all, you think about what's involved in that. It doesn't sound too hard, right? Well, brand new board with a brand new software, with brand new display, brand new keyboard, because this is a cheap one. We don't want a touchscreen or anything like that. And so you have to really get the hardware working just for the regular interface. The next step would be, all right, now make a call that you just dialed or typed in. And so that would exercise a different part of the hardware and some additional software. Then the next V might be, and now let's see if we could receive a phone call. It kind of tests another part of the functionality, that being the software receiving a phone call and being able to display caller ID. And then there might be an additional, maybe your really simple thing has 10 numbers for a address book. So test out entering in 10 numbers and dialing one of those numbers. So each iteration will go through the complete V cycle. Then there's spiral, which could be very similar to this, except that you're doing design as you go along. So you haven't fully designed the product. You are you're going through and building a prototype, testing it, having people look at it, and then you kind of do it again, add more functionality and make some changes. Do it again, add more functionality, make changes, and eventually you'll come out with something, and each time you go through, you add more functionality, you do more work, you ask people to test it. Then there's Agile, which has repeated sprints. So you have a block, and this is typically for software only, although I've heard some use this for hardware development as well. You have a chunk of software that will be developed in the next 3 weeks, tested, designed, programmed, tested, and implemented, and shown to the user or the customer. The customer will make recommendations, and then your next sprint includes changes according to what the customer wanted to see, and additional functionality that you're supposed to deliver eventually. But what it is you actually have a deliverable every 3 weeks, and it's pretty neat is you actually see success as you go along, and you don't have the ta-da environment. You know what that is? You do all the work, you hand it to the customer, and you say, ta-da! And then the customer looks at what you did and said, it's kind of close to what I wanted, but not exactly. And it's really good to get input from the customer way up front, and actually as you do the work, so that you can make adjustments. I talked about this. There are prototypes in which you do something that inherently may get thrown away, but it may also be used for learning. So I'm sure that when they came up with the iPhone originally, they tried a bunch of different things. Let's try an iPhone with a hard drive inside. Oh, that works really badly. All right, now let's do it with solid state memory. Oh, that works better. So in conclusion, software development stages, as I've discussed, going through requirements, design, peer review, detailed design, implementation, software testing. Make sure you follow at least those in the specific order. In other words, you want to make sure you do the requirements before you start doing your implementation. Thank you very much.